Okay. Now, since we have completed heat engines, now we will move to refrigerators. Okay. Uh, Only by understanding refrigerant, then we will be able to understand the second statement of second law of thermodynamics, that is the closure statement. So refrigerator, what exactly is a refrigerator doing? So you in a refrigerator, what it does is that this also works in a cycle, this refrigerator. So refrigerator, so you can see that various devices here. Uh, so this works in a cycle. Here the working fluid is your refrigerant. Okay. So this refrigerant undergoes a cycle. During this process, it will absorb a heat, that is QL. Okay, QL, and it will reject QH to the warm environment. Consider your refrigerator, it will absorb heat from inside the refrigerator, and this transfers heat to outside environment, that is QH. See, this is done with the help of a work. By supplying work from outside, you can see your compressor. We are supplying the work to the compressor. Without compressor, refrigerator will not work. So this is the work you are supplying to a refrigerator. So refrigerator, what it basically uh, does is that it takes in heat QL and it rejects QH to the warm environment by taking in a work W80. Okay, so let us understand what is the desired output and required input. Okay, so first let us see, for a refrigerator we don't define efficiency, but instead of efficiency we will determine something called COP. COP means coefficient of performance. Okay, this is what you mean by coefficient of performance. And what is the definition of coefficient of performance? Okay, for an efficiency you have work output by work input, by heat input, but here what is the required output here? Required output means, for a refrigerator, as far as refrigerator is concerned, you are taking in heat QL. So this is a required. See how much heat you are able to take in from the refrigerator space. That is your desired output. If you are able to take in much more heat, then the COP will increase. Okay. So this is the required output by required input. Required input means W net in. So that means the heat. So this is the only work you are supplying to your refrigerator. Energy you are supplying to the refrigerator. So this is the required input, that is W net in, QL by W net in. So this is the COP of the refrigerator. Okay. So for a refrigerator we don't have efficiency. We only use the term called COP, that is coefficient of performance. This is defined as the desired output by W net in. This point is very important, desired output. So this W net in, again according to first law of thermodynamics, you have W net in is equal to QH minus QL. So that means COP of the refrigerator can be written as QL by QH minus QL. Okay. So this is a refrigerator. Now you can see this is a practical refrigerator that we use. So for a practical refrigerator, you have an evaporator, you have a compressor, you have a condenser, and you have an expansion valve. Okay. So in a refrigerator, uh, how it works? So you have the refrigerant. So there is a refrigerant flowing through these devices. Refrigerant here will be at a liquid state. This is at a liquid state. So when it passes through the evaporator, it absorbs heat from this refrigerator space QL. It absorbs heat QL, and then so when it absorbs heat, it will become, so liquid refrigerant will be converted to vapor, and this vapor is passed through a compressor where it will be compressed. That means you are supplying the work. So it will be heated to a high temperature and pressure, and then it passes through a condenser where it releases heat to the surrounding medium such as kitchen air, that is QH. Then it passes through the expansion valve where the pressure is reduced. Pressure is reduced and it will become a liquid refrigerant. comes a liquid refrigerant and then enters the evaporator. Okay, so this is how a normal refrigerator work. It's a vapor compression system. So here W net in is equal to QL minus QH. Now, see, once we have understood refrigerator, we need to understand what is heat pump. Heat pump is similar to refrigerator, but instead, heat pump is used to heat the uh, room. It's not for cooling the room, but for heating the room. It is particularly used in cold climates. You can see that you have a warm indoors at 20 degrees Celsius and outdoor it is 4 degrees Celsius. Okay, what we are actually doing is you are taking in heat QL and you are supplying work. See, this heat pump works exactly the same way as that of the refrigerator. It takes in heat W net in and rejects heat QH, that is here 7 kilojoule to the warm indoors. Okay, but what is the desired output here? See, this device works, this heat pump works to heat the warm indoors. So your desired output here is QH, not QL, because we are trying to warm indoors, not we are not trying to cool the cold outdoors. We are trying to warm the warm indoors. That's why this is very important. QH is equal to 7 kilojoule. So this is your desired output. Now here, look, the COP of this heat pump, it is not the heat pump, is it defined as, sorry, this is for a refrigerator, it is QL by QH minus QR. But for a heat pump, see, look, heat pump, this is desired output by required input. Here the desired output is QH, not QL. Okay, because we are trying to warm the room. Okay, so desired output is QH divided by W net. So COP heat pump is equal to QH by QH minus QL. So again, according to first law of thermodynamics, you can write that W net in is equal to QH minus QL. So that means if you subtract COP heat pump minus COP R, this is equal to QH divided by QH minus QL minus QL by QH minus QL. So this will be equal to what? Okay, that means COP of heat pump minus COP of refrigerator will be equal to 1. So COP of heat pump will be equal to 1 plus COP of the refrigerator. So it will always have a higher heat pump than the same type of refrigerator.